this session, we talked about a word, how to represent these building blocks of natural languages, words, sentences, paragraphs, documents, represent them in a vector space representation so that they could become input to machine learning models. Once we can do that, it opens up the door to classification, regression, topic modeling, clustering, and so on and so forth. So we gradually covered 2-3 approaches. Words could be, we could do one-hot encoding. Then sentences and paragraphs and documents could be just some form of summation of those words. Either you concatenate those word encodings, one-hot encodings, or you sum them up, aggregate them. And so, for example, you can get the count vector, or you could just get a unique vector by concatenating those word vectors. Then gradually we came to a different document representation in which we replaced the word count with instead it's TF-IDF, which is more representative of what this document is about. You can look at the vector space and tell that this is about Cheshire Cats, or this is about the politics, and so on and so forth, right? So TF-IDF was good. There is a problem though with TF-IDF. It is not very context aware. So see, in language, the proximity of words matter. We tend to put Cheshire and cat together, but we don't tend to put, for example, a truck usually together with back propagation. Right? So for example, if you wouldn't, when you're talking about transportation, let's say that there is your brother or your sister is an entrepreneur dealing with a lot of trucks and logistics and picking up things and having them shipped to some other place and this and that using trucks. So the vocabulary or the sentences that your brother, sister, or your entrepreneur would say are very different from the words and that you would use if you're talking about, let's say, Cheshire Cats, or if you're talking about machine learning, AI, and backpropagation. The vocabularies would be different. And so it raises the question that, see, words don't exist in a vacuum. One-hot encoding is not a good representation, because the dot product between any two words is 0. Remember, we noticed it. And the Euclidean distance between any two words is always square root of 2. That is not particularly useful. We want a vector space representation in which words that go together in sentences and documents tend to go together. They also show up in the vector space representation next to each other, right? So twin words like Cheshire Cat should be next to each other, right? A king and a queen should be next to each other, relatively speaking, compared to a king and back propagation. Are we getting a sense? So can we have a vector space representation that looks at the relationship between the words? And so there are a few approaches that do that. And we're going to talk about those approaches. They search for a different a vector space where relationships are captured. So I will start with that. So let me put the main idea there. We want a vector space that captures the semantic relationships between words, right? So for example, we should be able to say things like king and queen are near each other, whereas a word like king and backpropagation are not words that are near each other, isn't it? In some sense. we need things like that, for example. So how do we create such a vector space? Right? We search for such vector space. Let us search for a vector space representation that captures word relationships. Now, notice that when we create a TF-IDF, we absolutely did not use machine learning. That was a basic statistics. Do you agree, guys? When we did TF-IDF, it was just bean counting. You just count the frequencies of things, and that's it, of words, and in how many documents they show up, and so forth. You get that. But now we are saying, can we look at the corpus of words, because a corpus of documents is a corpus of a lot of words and their relationships, right? In a sentence, words, they don't exist in jumbled up order. They exist next to other related words, isn't it? So, for example, when we say the quick brown fox jumped over the lazy dog, quick brown fox, these words are related, right? We are likely to say them together, isn't it? So lazy dog, for example, or when we say the cow jumped over the moon, there is a relationship between words. So how do we search for that relationship? The way we do that is we take a classic machine learning approach. So what is the machine learning approach? It is this. You say, all right, let us imagine that we have that vector space. You work from the solution backwards. So you say, first of all, assume that such a vector space exists. How many dimensions do you want to make it? So pick a dimensionality. A very common dimensionality that you may pick up is like 300 or 500. This is very common to do so. Now, a dimension space. And then you realize that that is a huge reduction compared to the initial vector space where a word was represented with 10K dimensional vector, right? If the word was one hot encoded as a 10K dimensional vector minimum, or 100K dimensional vector, or a million dimensional vector. But you're saying let each word be represented by a vector. So suppose you have a word vector, initial vector, V input for a given word cat. You want to map it to another word, let me call it E of cat, right? E vector. Now this E vector belongs to a much smaller dimensional space. Let me just call this dimensional space the embedding dimension. Let me use a little word D prime, right? And this is D. So you're taking V input belongs to our D, and you're mapping it to another vector, and you want to create a one-to-one relationship to another vector and get a simpler representation. So you say, well, don't you lose a lot of the information when you do that? And the answer is not necessarily. You don't lose information. So see, the intuition that we all carry is that if you take a two-dimensional picture of a three-dimensional object, you lose information. You take a building, you take an architecture. It's a three-dimensional object. You take a picture of that using your camera, you lose information. Now you can only see the side that you were seeing when you took the picture. The three-dimensionality of it is lost. Are we understanding that, guys? Huh? So whenever you come down, when you represent something from a higher dimension to a lower dimension, you're projecting down. And the most natural question that you would ask is, are you losing information? Right? And the counterintuitive answer, I suppose, in some sense, or the surprising answer is that not really. You, in fact, don't lose any information in that process. Now, the thing is, how could that be? That would be something interesting to think about. How can we project something down? How can we, a project is like looking at the shadow of something, or looking in the mirror, in a lower dimensional mirror at something, and how can you not lose information? So I'll give you a different example to show that you can actually do it without losing information. So let us say that in a painting, if you think of a painting as a narrative, let's say that you have a painting or image, and let's take a simple image, a 4x4 image. Well, a 4x4 image, right? Now, each point here, you think of it as a word, each pixel. So word mapping to a pixel, right? Image, the document is essentially, word is this. Maybe your sentence is each row if you want, and document is in the vocabulary of language, the document is the image itself, right? The full image, all these words, all these pixels put together. So if you look at a pixel can be represented by some color, isn't it? Now, your modern televisions, modern LCD screens, they contain approximately 32 million colors. Are we together? There are approximately 32 million colors that a typical LCD, for example, the monitor that on which you are watching me at this moment talk to you, probably can show 32 million colors, right? Somebody who is in graphics or web design, please correct me if I got that number 32 million right or not. Right? I'm just remembering from what I heard. I might be wrong. Maybe it's 3 million colors or something. It doesn't matter. It's a lot of colors. So every pixel, if I look at this word W1, the W1 is in effect a value. I can one hot encode it. Of all the 32 million colors, it is that one color and not any of the other colors. Zero everywhere else, right? So maybe this is the salmon color, right? W2, let us say, is the second pixel happens to be, again, somewhere there's a 1, 0 everywhere else. And let's say that this is a midnight blue. Are we together? So you realize that each of these colors, each of these so-called word, in some sense, in the image, is one hot encoded, very much the way we one hot encoded the words in the vocabulary, isn't it? So you can say that the vocabulary of a painting or an image is made up of 32 million colors, and any one pixel could be any one of those colors. Is that looking familiar, guys? Is that an equivalent way of saying?
Yes, sir.
Simple, right? We agree. And yet, now, suppose I ask you, do you store pictures or images, you know, the GIF, RGB, I mean, PNG and all of these formats, do they really store each pixel as a 32 million dimensional vector, right? So think about it this way, WI belongs to a space that is 32 million dimensions, right? Dimensionality is this much. That's a massive dimensionality, and it would take a massive amount of space to store it. And we know from experience that's not what we do. In fact, each word, each so-called word or pixel can be uniquely defined by 3 components: how much of red it is, how much of blue it is, and how much of green it is. Isn't it, guys? Right? 0 to 256, 255. This is again 0 to 255. And this again is 0 to 255, right? A very small integer space, right? And maybe if you want to be generous, you can also include an alpha channel, which also will take on a value from 0 to 1. The transparency channel. This is the transparency: red, blue, green, transparency. Are we together, guys? That actually a pixel can be represented in just a 4-dimensional space, or traditionally just a 3-dimensional space, RGB space. But when you represent a pixel not by a 32 million dimensional vector, but by a 3-dimensional or a 4-dimensional vector, are you losing information? Ask yourself. Are we really losing information? Let's think about it. Would anybody like to volunteer an answer?
No, we don't lose.
What's represented?
It is a complete representation, and it is a complete representation because there is an underlying relationship between colors. In the language of natural language processing, you would say that there's some semantic relationship between all the colors. They are not just haphazard. Right? For example, the salmon color and the Indian red color and the red color and the orange color and the brown color, they are fairly adjacent compared to blue, light blue, ultramarine blue, midnight blue, and so forth, which are themselves close to each other. So there are relationships. And not only that, because of the theory of light, which says that out of 3 primary colors, you can manufacture any color, right? Therefore, you get away with it. Right? Therefore, you are able to do a complete representation just using a 4-dimensional space. Now, if the theory of primary colors and lights coming out of primary colors were not true, then the story would be different, right? Then the stories would be really different. But that is what gives us. And so, in other words, between the colors, there is a structure that helps create the words. Now, in language, we of course know that words are interrelated through the semantic structure. So we ask ourselves, therefore, in the same way as a picture can be represented with just 4 dimensions or 3 dimensions, rather than 32 million dimensions, in the same way can we represent words in a lower dimensional space and still not lose their semantic meaning. In fact, not only not lose, but gain semantic relationships. We live in a very high dimensional space where every 2 words are perpendicular to each other, practically, right? Every 2 words, if you think they're perpendicular to each other, right? So you can think that, that square root of 2 is very interesting. If you think about it, imagine that you have a x-axis and y-axis. One point is at unit distance 1, and one point is at a unit distance along the y-axis, a and b. What is the distance between a and b? It will, of course, be square root of 2, the Euclidean distance. And 0 for cosine distance between this vector and this vector. Do you see that, guys? No. So every 2 words are perpendicular to each other when you think about it in this one-hot encoding space. So if all the words are orthogonal to each other, the relationships are simply not captured. Whereas we want a lower dimensional representation, typically 3 or 500. You pick your dimension, you can pick 100 or whatever, a dimensional space, and say, can I project all the words down to these dimensions? And that dimensional space is still very rich. What you're saying is, can each word be represented by, let's say, a smaller number of dimensions, 300, 500, real attributes of those words, linguistic attributes of those words, or semantic attributes of the words, such that the relationship between words are captured. And that is a pursuit. So when you do that, the word that people use in this literature is embedding, word embedding. Word embedding. Word embedding, in other words, is a projection, is lower dimensional, lower. People often use lower dimensional and more mathematically rigorously, people will use lower rank representation of a word, of words, right? So let's do that. So the traditional machine learning way is, if you say, what is the relationship? How can I do that? You start with a very simple way. You can say, hey, take words, each of the words, WI, and to each of them, just assign some random values of 300 dimensions. Let's say, I'll work with 300. I don't want to keep saying 300 or 500 or whatever. I will just, or let me just say D prime, right? D prime, where D prime is, for example, 300 or 500 or whatever it is. So in this, so one easy way is to do this. You take a vocabulary of words, and each of the word is, you realize that the word, each of the word is, let's say, 10K dimension. They are, because they're 10K words, you will start with ard, what, or whatever the first word in the vocabulary is, right? And you will go with Z, Z, Y, whatever last word of the vocabulary is, right? I don't know what the last word is, but the last word that I know is probably zygote, right? So let's say you go from aardwork to the zygote or something like that, right? Now, each of these words, you are saying that you're representing it. So how many, what is the height of this? This is 10K. Now, this is D prime, right? The dimensionality or the number of cells here are that. So you say that, see, suppose I start with a situation like this, a matrix like this, such that each word is represented by this. And then what is it? If it was perfect, if we had, let me put some values here, these values, if we had perfect embedding vectors, then, for example, let's say a daffodil would be closer, is near iris, but far from, let us say, a scissor. Things like this would be true. Are we together, guys? Right? Suppose we had successfully done it. So now the problem becomes, how in the world do we populate this with the right values? How do we, what are the right representations for each of the words? So there are many algorithms that people use. They all depend on one basic idea. You feed it sentences. When you have a sentence, let's say you have a sentence, I'll just take a line from, since we talked about daffodils, I'll take a line from a poet, a British poet, Wordsworth. It is, there, breathes. It is my faith that every flower enjoys the air it breathes. Right? Again, it's from Wordsworth. For lack of any other sentence that would occur to my head, this one popped up, so I put it here. Now, you can look at this and say, you know what, can I predict the next word, or can I predict that these two words, these two, do you see that they tend to go together, right? Flower enjoys, or they these words are much more likely to happen together in this sentence, and perhaps in many, many sentences. We all breathe air. If you look at this sentence, these two words, the proximity in this sentence is reflective of the general proximity of meaning or the context of air and breathing. Would we agree, guys? For example, it's unlikely to be a sentence that it is my faith that every flower enjoys the air it scissors, right? That is unlikely to be there, or horse, some things like that. So we start with this, and we use as a proxy, or the fact that empirically words that are related, they tend to be proximal to each other in sentences. So far, so good, guys?
Yes, sir.
Yeah. So then almost all algorithms that find or search for word embedding, they have an implicit assumption that a proximity is a good empirical evidence of semantic relationships, right? Of nearness, semantic nearness. And they exploit this fact. So there are many, when we do the natural language processing month, 1 month of natural language processing in this workshop, as we move forward, we will do many of these algorithms in detail. And they are continuously coming. I'll start with the earliest one. I believe it showed up in 2013. It is called Word2Vec. Right? So one implementation is Word2Vec. It's a very good embedding. It's a very popular embedding of words. So how do you generate this? You can generate it in two ways. Either you take the general purpose corpus, like so people have created massive corpus, Stanford University and this and that. They have created large corpuses, for example, of English text. Every country has created a standard corpus of lots of documents in specific languages. And you can therefore look at a proximity of words across the massive amount of sentences in those languages, right? And therefore, you can learn word embeddings from that. Or alternatively, what you can do is you can hand build your corpus and do that. And there is a third way of creating embeddings, which we won't go into here. You can create an embedding implicitly in the process of doing something else as a side effect. For example, you're writing a classifier of words, but you feed it initial one-hot encoded words. The first layer is there is an embedding, and you train the embedding as part of your journey of training a neural network to classify the words into something, you know, the sentences into something. For example, whether it's about politics or it's about physics, right? So things like that, you can do that. But today we'll start with the original one, the Word2Vec. It turns out that the Word2Vec itself has two popular representations. It has the bag of words, continuous bag of words, and then the other one is the called skipgram, with actually the people often just call it skipgram, but the full technical spec is the paper is a skipgram with negative sampling. Right? So now these are rather big words. I'll just talk about it in very simple words. The continuous bag of words I won't do, because today we have limited time and we would like to do one properly. So I won't do continuous bag of words except give you the basic idea of how to do it. So look at this sentence. Suppose I could give it is. Let's take a window size of 3 arbitrarily, and people often take odd size window sizes. And you say, suppose I fed in it is, then input. So imagine that you could write a sort of a predictor, right? A classification engine that could say it is, if your input is x1, x2, so imagine that you have a two-dimensional feature space, right? It is, well, actually not two-dimensional, but it's higher dimensional. But so let me not say whatever the initial dimensionality is, that it is, you should be able to predict my. You should be say, is my, should predict the word y. So think of it as y hat or y that you want to predict, that label that you want to predict. It is my faith, right? My faith. These two should predict the word that. Do you see that? What you're doing is you're sliding a window through the text. You first slide it here. The next position you put it at is this. And the next position you put it at is this. And you always take the first two words or 3 words or 4 words, whatever it is, as your predictors, and the last word as that which is predicted, right? So you can move forward with that, but it has one limitation because of which it is not so much preferred these days. It is that it is a directional process. What do I mean by that? If you look at this, suppose I create a sentence like, when I went into the meadow, I met a happy cow. Now think about it this way. Suppose you have a prediction window like this. Suppose this word happy wasn't there. It is, I met a cow, right? If I had not left it like that, I would have, suppose I had given this problem to you, meta, what? You would probably have guessed in a meadow, what do you find in a meadow? Oh, you find a cow. You would have said cow. But if I had given it to you like this, I met, the whole sentence, I met a space cow. Now you know that you can't fill in a cow here. A cow would not make sense. So now you're forced to pick some adjective to a cow. You can say a big cow, a happy cow, or whatever it is. Then you're no more likely to say a cow, but you'll say happy, right? So now there comes an interesting issue that, see, if you just slide the window forward, then your predictions are not as good as when you look at the word beyond the blank that you're trying to predict. In other words, a word on this side matter as much as word on this side, right? So when you are sensitive to words on both sides of a word, of a particular word, the context word, then you take a slightly different approach. You say it is not whether it is on the left or the right, or before or after that word. I want to say that, let's say that we are looking at the word happy, right? The word happy coexists with these words. Let me take 2 words after that. Actually, let me take a word which has a lot of neighbors. Let's take this word meadow. That then you can create a window. Let's say that you take a window, and I'll take a window that people take in practice. For example, the GenSim library takes a window size of 5. GenSim is one of the libraries. 5. Right? So what you would say is the word meadow, you would create a table like this. Meadow, meadow. If you have the word meadow and you have the word the, you did encounter it in the sentence, you give it a label y, think of it as x1, x2, and this is your target, y is 1, your data. If likewise you can say meadow, I, 1, right? Again, meadow, met, 1. So these are the combinations that you did actually find, right? And so on and so forth. Huh? Now you say that suppose, let's be clever. Suppose we write a classifier, right? We assign word vectors in such a way that if I ask that in this, suppose you have some form of a word embedding, what is the likelihood that this word and this word, they will be neighbors, right? So it will say, yes, I can create an embedding in which these two words are near each other, and this word is near each other, and this word is near met, and so forth. But then if you try to train that network, the neural network will be clever. It will soon figure out that all it needs to do is give every word exactly the same word vector, because then every word is similar to every other word, and it will match all your situations, right? Because all of your positive test cases where you're assigning the value 0, it will match. So to break this, what you need to do is, whenever you take a word, let's say you take a word meadow, and you take the word the, right? Or meadow and met. Let me take something, met, right? And you give it a value 1. You then do another thing. You take the word meadow, and then you replace it here with a random word from the vocabulary, right? So for example, you can put the word, I don't know, backprop. But now we know that meadows and backprops are rarely ever mentioned in literature together. We are probably the first ones to do that in this session here. So you would put a value 0. And then you would do it again. You put a few negative samples, meadow, and let us say, what else can I put? I put medicine, right? 0. Again, you would say meadow, and let's say you put, I don't know, suitcase, 0. So this is called negative sampling. Negative sampling. You have created a lot of negative samples, right? So this particular approach, it is called skip-gram with negative sampling. There are 2 hyperparameters. So let's acknowledge the hyperparameters here. One hyperparameter is window size. Window size. So how many elements on the left and the right? So suppose there's a word, how many elements on the left and the right will you take? So you usually pick the same number on the left and the right. So you would realize that your window size will always be odd, right? Because if this is the same as this and this guy is sitting in between, you will end up with an odd window size. So your window size is a hyperparameter. A common value that these libraries tend to take is 5. But you can play with window sizes. And they have certain implications. Since we don't have enough time at this moment, we'll do it when we do natural language processing in depth. We'll talk about that. The other hyperparameter is how many negative samples for each positive sample. So you need to pick a number, 3, 5, whatever it is, or 3, 4, 5, whatever. Pick your number. How many negative samples are you going to produce? Right? Now that you have produced this negative sample, you realize that the neural network cannot play a clever trick and immediately just give all the vectors the same value, because then these two will not be orthogonal to each other. Meadow and backprop will not be perpendicular to each other. Isn't it, guys? Do you see that?
Yes.
Yeah. So it's common sense. So now comes the whole process, the mechanics of it. And the mechanics is actually extraordinarily easy after this. So once again, I will just go and say, what you do is you take two, like actually only logically in your mind, you think of it as two. So you write all the words, your art, work, right? And what was the last word I took? Maybe Zephyr, P-H-Y-R, Zephyr, or something like that. And so each of these words, there are 10K of these, let us say, and I'm taking a small vocabulary. And this is your D prime. Let us say D prime is 300 dimension. What do you do in the beginning? You take, this is your embedding, think of it as a rubric or your matrix. This is your embedding matrix. In the high tradition of deep learning, initialize it with random values, right? Pick any random values you want. So this would be a lot of, this is literally embedding weights, right? So you pick some random values everywhere. Do the same thing, logically speaking, with another, imagine that you have another matrix. I'm just writing it down as a, once again, exactly like this. You put the same works here, art, work, Zephyr, Zephyr. This we'll call it the context matrix, right? Context matrix, context weight, so whatever it is that you go and randomly initialize it. Right? So let me write this word down. Randomly go initialize it. Now do this. Now the process is quite simple actually. What you will do is, suppose you have the word, this word is there. Let's take the word. What are the, meadow has the word met, backprop, and medicine. So let's take meadow. The word in context is meadow. So let's just say that this is the word meadow, right? Somewhere in here is the word met. Somewhere up here is the word backprop. And somewhere in here is the word medicine, let's say. And somewhere way down below is probably the word suitcase. Well, I didn't keep enough space for suitcase. So let me say suitcase. So suitcase is here, right? So now what can I do? We play an interesting game. We take the word meadow here, meadow, and you will dot product with every word that it was associated with. So now I can create a dot product with the backprop, for example, right? So remember guys, this is a vector and this is a vector, and I can do the dot product. Remember, I tend to write a vector A dot B that you would write. I often write it as A comma B, right? Just to make it very explicit that I'm taking the dot product or the inner product. So the nature of inner product is, if two things are aligned, vectors are close to each other, the inner products would be high, right? If on the other hand, they are completely orthogonal, they're unrelated, then their dot products will tend to be zero. And then you can also have opposites, love, hate, and things like that. Right? So now what you do is, now we'll start the game of the learning, the machine learning game. Remember, what is machine learning game? The learning part of the game is this. This learning part is this. What we can do is we go back to our table, and let me just reproduce this table here so that we can, let me just for a moment shrink the size so I can see it. Okay. Meadow met, meadow backprop, meadow medicine, and meadow suitcase. Meadow met, Meadow backprop, Meadow medicine, Meadow, well, this is Meadow suitcase, right? And remember the Y values that we gave was 1, 0, 0, 0. Now what you do is you put this X, this word, and let me just call it X1, X2. You take the, what you do is, you know that you have represented this as an embedding vector, E1 and E2, right? For each of these words, meadow, there is an embedding vector. You can go look up this embedding vector here. Where is the embedding vector for meadow? This is, let me write it here. This is the embedding vector for meadow, right? This is the embedding vector for medicine. Likewise, this is the embedding vector for met. This is the embedding vector for suitcase. So now what can we do? We can look at the dot product of these embedding vectors of meadow with everything else, right? Or of every first column versus second column, because it wouldn't just contain meadow. As you move your window around, there would be lots of dot products that will emerge. So what will you get? You will get, if you look at the cosine distance, you will get numbers. You'll get some numbers, right? So meadow, met, maybe, let us say that this is 0.7, backprop is 0.01. This is, medicine is, let's say, minus 0.3, and meadow suitcase is 0. I don't know, I'm just cooking up numbers, huh? 0.5, something like that. You get this. The word people often use for something like that is, this is the raw energies that you produce. Then you do something else. You either do sigmoid or you do softmax. And what it does is, it will amplify the biggest of them. So what will happen is, maybe this will become as a probability, it will make it as a probability. It will become a number between 0 and 1 in both these situations. So it doesn't matter, I'll just write sigmoid here. It will become, let's say, meadow met will be, I just said 90%, right? This will be like 3%, right? And I don't know, so on and so forth, small numbers. Are we together? So now you got this is your Y hat, right? You got your Y hat here. And now the next thing that you do is, here, actually I should write this here. So between 0 and 1, these are probabilities. The last thing you do is, you find the error here. So what is the error? Error is this minus this, Y minus, this is your Y hat, right? These are your predictions, Y hat. Remember, we always compute error as Y minus Y hat in a standard classification problem, right? And so this begins to look like what? 0.3. This begins to look like, I don't know, 0 minus 0. Minus, this is 90%. So no, 0.1. The error is 0.1. This here, the error is, what is it? It's pretty big, 3%, 0. I don't know, 97, 0 minus 3%, minus 3%, and so forth, right? You can get the numbers here. You treat these as your errors. Now what do? All you need is a loss function. If you remember, all that we need now is a good loss function. And because we are talking about sigmoid or softmax, a good loss function would be cross entropy. Cross entropy loss could be perfectly good, or any other, you can go cook up your loss function. So guys, it's a very long chain of reasoning that we are following. I hope you are with me. It's a very simple reasoning though. Now we have errors. In machine learning, the moment you have a way to quantify errors, you know that essentially the war is won, isn't it? Because the moment you have a loss errors, you can write a loss function. Any sensible loss function you can cook up. The moment you can cook up, now what can you do? You can apply gradient descent, the standard gradient descent processes. And ultimately, what can you do? You can shift, you can change the weights using gradient descent of all these weights here. You can change till the next time, the next epoch or the next iteration that you do through the data makes the errors smaller. Do you see that? And at the end of it, what will happen is this matrix of values would have reached a situation in such a way that the dot product between the vectors of words, between words that are proximal to each other or tend to be proximal, will be much smaller than the dot product between words that tend not to be proximal to each other, right? And so now you have created a vector space representation that you were searching for that is context aware. Do you follow this reasoning, guys? It's a pretty clever, it's straightforward reasoning, but it's pretty clever. And so what you are doing in effect is you're taking a vector. If you now turn this argument and see what you're doing, you're taking a vector which is a 10K wide and you're narrowing it down to a smaller vector. You're to a D prime is equal to just 300 a dimension vector. So for every word Wi, there exists an embedding vector of Wi, which only belongs to a lower dimensional space, right? And when you do that, this is when, you know, something most remarkable happens. This was first done, I believe, by Google researchers in 2013. Around that, they were starting to come out with the word embeddings. And what happens is you start seeing relationships which actually are so spectacular that you wonder that, you know, you hoped for semantic relationship, you know, the relationships between words to emerge. But it completely sort of exceeds in the beginning. When it came out, it exceeded everybody's wildest dreams of the relationship. It was just absolutely fascinating what they found. And it was the beginning of a very high quality embeddings for vectors. So the state of the art has moved forward. Today, we do even better embeddings. We will use transformers to do embeddings, BERT embeddings, and so on and so forth. So in many ways, the Word2Vec, the glove, and all of these are beginning to, you know, they're becoming very mainstream, and they're beginning to look like classical word embeddings now. But still, they're very fascinating. So for example, you notice some interesting relationship. You see, for example, that king minus queen is equal to, the difference between these two vectors is the same as difference between man minus woman vector. So if you go and look into the embedding space, not exactly equal, but approximately equal, so that you can say they're practically equal. And it's very fascinating to see this relationship, because what it implies is you can say that a queen is king minus man plus woman vector. And in some sort of a very intuitive way, it is both delightful and it seems to make sense, isn't it? You start seeing other relationships. For example, you notice that you could say things like USA minus Washington is equal to, let's say, India minus X, right? And so you can say X is equal to, well, India plus Washington DC, let's say, DC minus USA, right? And so what you're saying is it's relating a country to its capital. So suppose you did not know the capital of India, you could actually write this equation, go to your embedding space and see what is that word which is closest in value to this. And when you do that, you will find that the word is New Delhi, or the phrase is New Delhi happens to be closest to that. And the same thing will work with UK and London and so on and so forth, right? And that is the magic and the power of word embedding. So now what we do is we have now discovered a much more powerful a powerful embedding or vector representation of words. So word embeddings are a powerful and semantically aware representation, vector space representation. Now this has become a given. You take a word, right? And you first thing you do is you convert the word to its embedding vector, and then you work with that. So suppose you have a sentence, well, you can again do what you did with bag of words. You can put the sentence as just adding up all the embedding vectors or concatenating the embedding vectors. So one of these two, you can go ahead and do that. You can do the same thing with documents. Are we getting that? And that becomes the input to your classifiers, your regressors, your clusters, and so forth. So, and these things are real. With these things now, for example, we can do sentiment analysis. We can do something called language model. Language model is predicting the next word. So for example, have you noticed that when you're typing on your cell phone, on your smartphones, you type a few words and it pretty much keeps guessing the words that will come afterwards, right? That you're likely to type. So that is again word, that is called a language model. And you can very clearly see where it is coming from. The roots of it starts with a good word embedding, right? Because word embedding is exactly that, is the relationship between words, right? It can tell which is the next most likely word you're going to have, because that is exactly how your embedding was trained in the first place. So guys, today we covered a lot of territory. We have 10 minutes left before it is 10 o'clock. I would like to review what we learned. In the first half of this today, we learned that we need a vector space representation for language, for words, sentences, documents, paragraphs, and so forth. We started with something very simple, one hot encoding of words, and gradually we started refining and getting somewhere. Then we realized sentences could be written as word concatenations, word vector concatenations, or word vector summations. We realized that we can do better. We can do TF-IDF vectors. Now remember, when we do TF-IDF, it is a word. It is about a word in a document. So there is no such thing as a globally correct or value of TF-IDF for a word. So you take a word, let's say the word horse. It will have a different TF-IDF in one document versus another document. Right? So TF-IDF is document aware. So what TF-IDF gives you is that when you look at it as a vector, a document becomes a vector, right? Where each of the word placeholders contains the TF-IDF of that word with respect to this document. And so every document therefore becomes an input vector to whatever machine learning algorithm you want to feed it to. Right? So that was good. Now, one thing to note is that that is not an independent representation for word. People started looking for document agnostic. a word embedding that had special qualities. It was a lower dimensional matrix, lower dimensional representation. It was context aware. It was semantics aware. And so came this whole breakthrough of word embeddings. The first one was Word2Vec, which has two representations, a continuous bag of words, which is sliding window forward, or the other one, which is skipgram with negative sampling, right? So I taught you skipgram with negative sampling. Now, when you really think about it, it's quite easy. Once you start representing words like this, you say, in the meadow, I met a cow. Meadow met is together, but meadow backprop doesn't happen. Meadow medicine is not there. Medicine suitcase. So you just populate your table, your data set. You create a data set in which the positive cases you get from your sliding window, right? But your negative cases you get by taking the word and putting adjacent to it just a random word from the corpus, or the vocabulary, sorry, from the vocabulary, and assigning a value y of 0. So now you have a perfect data set. You're basically saying, what is the probability of these two words being together? 1. The probability of these two words being together? 0. That is the ground truth. And now you go and say that if these words were vectors, in this sense, embedding vectors, I want these embedding vector weights to be such that things whose joint probability is 1, the dot product should be 1. The probability of, I mean, not the dot product, but dot product then converted into a probability, relative probability, should be 1. Whereas words that don't go together, that were not evidently together, their dot product and their probability of joint happening should, according to this vectors representation, embedding vector representation, should be very low, 0, right? And it works out. The beautiful thing is that you are able to create the error, and see, once you can systematically quantify the error, once you take the dot product from there, you get the sigmoid or softmax, convert into probability, and then you see the difference in probability, y minus y hat, and so on and so forth. Then, you know, the battle is won. You already have this. You're trying to minimize it. There are many ways to do that. Cross entropy will say y log y hat summed over negative y summed over all the instances. How do you minimize this, right? So you have the y, you have the y hat. Y hat is this column and this column. And so this was only logically speaking that you're trying to minimize the error. The cross entropy function will be different, slightly different, y log y hat, and so forth. But the bottom line is that you will be able to write a coherent loss function. And that loss, the moment you can write a coherent loss function, you can do gradient descent. We are familiar with gradient descent. And the moment you can do gradient descent, therefore, what it does is iteration. As you step through iteration after iteration, it goes and fixes your matrix, you know, that embedding weight matrix. For all the words, they continuously get updated, right? And so after a few epochs of training, you have pretty much found the embeddings for all the words in the corpus. Right? And those embeddings now are a much richer representation of words. First of all, they're document agnostic. Right? You have created a representation that has been derived from the entire corpus of all documents. So the richer the information, the more likely you are to find true relationships between words. Right? So that is that. And these vectors, these vector representations, therefore, make the bulk of natural language processing. It reformulates the world of natural language processing back into the machine learning world of classification, regression, clustering, topic modeling, and so on and so forth. Right? And we will not get time to go into all these details. Today, as we know, this was the fundamentals workshop series. Here, my goal is to, as quickly as possible, introduce you to all the key architectures in deep learning. Right? We had 6 weeks. So this week we learned about the at least got started with the architectures for natural language processing. Tomorrow, we'll talk about something called a recurrent neural network. In that family, you have the simple recurrent network, and then you have the little bit more sophisticated sort of a downtown brothers of them, cousins of them, called LSTM and GRU. These are neural architectures uh, within the RNN family. We'll learn a little bit about them. These are auto-regressive models, which means that like time series, right? A stock market. The value today or the weather depends upon the prior values that you can use to predict it. Right? The words are like that. Language is like that. It's sort of auto-regressive. The word that will come next depends upon all the words that have preceded it. Right? So RNN was the first auto-regressive model architecture, neural architecture. Its refinements are LSTM and GRU. We'll talk a little bit about it, but I won't talk too much about it. The reason is I need to cover a much more important topic, which is quite dominant today in NLP. In fact, it's become synonymous with NLP. It is transformers. Today, when we look at natural language processing, it is dominated by two key ideas: word embeddings and transformers. It used to be that the field used to be dominated by recurrent neural networks. Right? So, but now recurrent neural networks are still used, but they are not dominant. Transformers are dominant. And before I close that and we go to tomorrow, I'd like to show you some resources on our course page, and so that it gives you some material to read about. And for those of you who have time, I would encourage you to go and listen to a couple of talks we have given. Let me go to okay, deep neural networks, deep learning fundamentals. All right, so let's go here, and you will find that NLPs after the loss. Remember, we have done the topics before that, loss, landscapes, and so forth. So NLP is a world in itself. These times, the universities are now very seriously considering having, see, as you know, these days, there is a master's in data science, right? It has branched off from computer science as a specialty of its own. But there's even further specialization. People are now beginning to give, some universities are beginning to give a master's in just natural language processing. So we obviously couldn't possibly have covered it in one evening. It is worthy of 2 years of study, a whole master's. It's a big field now, and a lot of activity is happening in this field. So to get you started, I put all these resources that you see. Hang on, let me increase the font size. Are you guys able to see that? So there is an old classic book which is being rewritten. I would highly recommend that, you should have one book which is sort of conceptually or theoretically rigorous. Just like for deep learning, we have the deep learning book by Ian Goodfellow and all this, the big guys. In the same way, one great book which is being rewritten in the third version is this book. It is still in the online stage. It is online and it's being written. I would strongly encourage you to go and start reading chapters. If you are really serious about NLP, get a head start. We will be using it in the month when we do NLP very seriously. We'll do that. Then there's some other people who have written some NLP books, NLP overview, not of the same high quality, but still pretty good. Here is some here. So this is an effort that is in progress that goes into, and you can review the topics that we covered. These are also being talked about in this book, your deep learning book, what we talked about. There are a few books which are more accessible. So one book that is very easy to read and accessible is this, Natural Language Processing in Action. I found this book to be like a very easy read, actually. You finish the entire book over a weekend at most. Right? So you can consider getting this book, especially if you know neural networks and so forth. After doing this workshop, you'll realize that you can pretty much skim through the first half of the book practically, pretty quickly, knowing PyTorch. And there's some other books, and I've mentioned those books here. Now, one in this world, so then there are some articles. Now I put some curated list. People have created some awesome, these somehow the word awesome seems to be there associated with it. There is an awesome NLP. It's a curated list of lots of NLP resources. I would highly encourage that you bookmark it, these ones. And it's a wealth of information that you can get here. Then you have awesome deep learning uh, for natural language processing, yet another curated list. Now, these people that I talked about who are writing this book, they also have a YouTube channel. These are Stanford guys, by the way, Stanford frauds. So they also offer the Stanford course. So this is it. Um, Natural language processing with Dan Jurovsky and Chris Manning. I would suggest that you can go watch these videos or certainly use it as a reference. Then besides that, there are some excellent podcasts, really good podcasts. Usually I don't think I've mentioned podcasts on any other topic, but here are some very good podcasts that keep coming up. It just shows how hot this field is. Then there is one website that I must point out and say is very good is Sebastian Rude's website on NLP. Excellent site. This is a site called Sebastian Rude, and he has a lot of things on various topics on NLP. Right? On many things, but certainly on NLP, he has it. Then you have, besides that, there is a, like if you want to follow on Twitter what is happening on in NLP, this is the Twitter sort of a channel for NLPers. Right? Continuously, something or the other keeps coming up. Right? So in other words, there's a wealth of information available out there. Another curated list for NLP is this. This is also a very good list. And when you look at this long list and the number of libraries that people have created, it's just absolutely amazing. It seems that you have entered a city that you didn't know of, and you're walking down the main street of a city that is bustling with life and creativity. That's the sort of sense you get. Now, NLP has many frameworks which are quite mature. The typical starting point people give is NLTK. I mentioned to you guys that NLTK is written in Python itself. It tends to be slow. There is a tendency everywhere to give tutorials in NLTK for a reason. It's very easy to get started, but it's big. Even simpler version is text blob. Remember in the first week, I started you out with text blob. It's fairly good, but then a more industrial strength library. So if you use NLTK, what happens is, for example, it doesn't have semantic aspects to it, topic modeling and so forth. Then you'll have to use Ginseng along with it, which is a bit of a issue. I mean, you would like to stay within the scope of one library rather than hop around. So that's that. So for high performance, Spacey is very good. And Allen NLP, which I like actually, is very interesting because it is based on PyTorch and Spacey, putting it together. Then Hugging Faces is about transformers. Hugging Face is the sort of the mecca of all transformer-based stuff. We'll talk about that tomorrow. So that is there. Now, Stanford's core NLP is very prestigious and very, very good. Written in Java, very powerful. There is a Python dialect of it also now. Then PyText is PyTorch and NLP putting together. Now, one thing that is not mentioned so often is Baidu. Baidu is actually perhaps the leader. If there's any one person, one company that is ahead of even Google, Microsoft, and Facebook, I would say it is Baidu. It's a Chinese company, but they're doing very, very well. Andrew Ng used to head the AI lab at Baidu for some time. After he left leading the AI lab at Google, he went to Baidu and left it. Now, of course, he's fully devoted to his Coursera stuff. So Baidu's earning. Again, a great site to go do that. Now, there is a there are a couple of things that I'll give you as reading. Today, say for NLP, the word embedding is important enough that it merits a section of its own. And they're very interesting embeddings. For example, if you have structure, hierarchical structures and so forth, you can use embeddings that are specific to that. Now here I've given an embedding called the Word2Vec, the illustrated Word2Vec. Please do take out time and review this. So the reading material I'm giving you is read Word2Vec in your books, but more than that, go and read this blog. This is the review that you should do as reading material. Jay Alamar has given an excellent explanation and very well quoted explanation of word embeddings. In particular here, he has talked about Word2Vec. Right? So do please go and play with these resources. Tomorrow will be a little bit of recurrent neural networks, mostly to beat up upon it and show its limitations. And then it will, in other words, be a straw man. And then we will move on to the transformers. And we'll have a bit of a session on transformers. Now, while I do that, if I may, and obviously at this moment, those of you who have to drop off, but I would like to show you some things about the power of NLP. So let's go to Alan NLP and let's see some demos. These are real utilization of this. So for example, this says reading comprehension, right? There is a particular model. These are all transformer, etc. based models. Let's take an example. You can enter your own passage and you can ask it questions. So for example, they give this example. Here is a text that has been entered. And now to this text, you ask this question: how many partially reusable launch systems were developed? And the NLP has to read this text and from that, figure out the answer. And the amazing thing is that when you run it, it will immediately come out with 2. And it just, do you notice that it highlights the word 2? Shows the power of where NLP is. And in fact, the power of transformers, etc. is. And if you ask it to interpret the model, it will give you the saliency of it, like where is it paying attention, right? What are the words that it used to decide? These are the words that it used to decide, right? So it can literally give you 2 partial reusable. It literally latched onto those words, right? And so on and so forth. And this speaks to the interpretability of the models. Very, very powerful. And you can literally see how far things have gone, right? You can take another example. Suppose you give it a picture and you ask this question: what game are they playing? So see the interesting part, right? This will ultimately come up with, it will run for some time, as you can imagine. This is computationally a little bit interesting. And it says that with 100% score, it is most likely baseball. Next is likely to be softball. Now, if you know these games, you probably would agree that that is what it is, right? And with lesser probability this. And you can, of course, upload your own image and do that. But this too is natural language processing, right? Another is named entity resolution, proper nouns, right? And so forth. So let's take an example. This is an example, and you run it, and then it finds out what are the proper nouns. Grandpa's Joe and deep learning, right? Do you see? And not always perfect. It came out with deep learning as a location, which probably isn't. Deep learning is a subject, but Grandpa Joe's is an organization. Pretty good thing here. You could take something else. You could do, it says Allen NLP and PyTorch are organizations. Allen Institute for Artificial Intelligence is an organization. Seattle is a location. So this one it got quite right. And you can play with that. Then you can take other things. For example, let's run this. And then it comes up with a statement published. It's published the theory of relativity in this. So it just finds out the pieces of the language, the temporal modifier and the parts of things and so forth. Sentiment analysis is almost both loved and hated these days. It is loved because where it works just very well. Where it doesn't work, like for example, it doesn't quite understand sarcasm. A lot of effort is going into creating ability to be sensitive to sarcasm and irony in sentences. But that is the frontier. Right? And you can see what is it doing that, you can ask it to interpret the model. A very well-made, entertaining picture. So it comes out with a positive sentiment because it finds the word entertaining there. Right? Then dependency parsing. It shows you the relationship between the parts. And this, of course, when we do the natural language processing in depth, I will explain to you where all of these things are. Semantic role labeling. I'm just giving you an idea, not necessarily explaining everything. So let's run that. And again, it's showing the semantic relationship. The key which is needed are related to modifiers to access the building. Then core reference resolution. Right? Refer to the same, like you find all expressions that refer to the same thing, right? So let's take one. You can see all the blues are referring to similar things and so forth, right? So that is that. You can do question and answer situations. Right? And so there's more to it. I'm quickly sort of running through textual entailment, decompose. So that it tells you whether one thing follows from the other or not. Entailment, that is it, right? So this is it. It is very likely that the premise entails the hypothesis, right? Here is the premise, here's the hypothesis, that they are related. If you help the needy, God will reward you. Giving money to the poor has good consequences. So you see that the two, there is a relationship between the two. Right? It finds out. Language modeling is, of course, completing the sentences. The sentence is this, Alan, NLP is, right? Prediction, the. So you can say is great. Now let's see. Great example, great tool, right? A great resource, program library. If I say library, immediately it says for. Let's go with the word for and see. For the, and so on and so forth, right? After a little while, things can get a bit lost. So that is that mass language model, and you can contribute. So Alan, NLP is, this was a good demo. I thought I would show you. So NLP is a very fast growing field, guys. What are people able to do? Let me give you an example, or 2-3 examples of the cutting edge of that. When people write legal documents, different parts of the documents are cut and paste from different places. Nobody these days is able to write a 400-page legal contract just from scratch overnight. But lawyers habitually produce or regularly produce such documents overnight. The way they do it is they take pieces from other documents, copy paste, and do it. The trouble with doing that is one part of the document may weaken another part of the document. The legal language may contradict each other and open loopholes for the violation of contracts and so forth. People are using NLP to find such areas. It is able to do that. One of the interesting frontiers of natural language processing is people do visualization, data visualization. Data visualization is a tedious thing. You take a group of people who sit and create those visualizations for you, or you sit and you write matplotlib and so on and so forth, and write code to create data visualization. All of you as data scientists have had experience with that. So how would you feel if I told you that there is already significant progress that you can give natural language commands? Say, give me a visualization of this from the data, right? And you give it the data, it will understand the data, and it will create the visualizations that you are looking for. And those visualizations are real. They are not just simple bar charts or so forth. They will create an entire dashboard. They will write your D3JS, your Vega code and so on and so forth. Everything they'll do it. And today we have natural language processing systems that can do it. And as you probably are aware, GPT-3, which is one of the largest transformer model, in fact, the largest transformer model, is so insanely smart. You say, I want to create a user interface which contains the ability to do this, input this and do that. And right away, it starts writing React code for you. Those of you who know UI framework know React. It will immediately start putting React, Bootstrap, and all of that. And before you know it, it has written a fairly credible and good user interface for you. And also bug-free. Right? So that just shows you the power of natural language processing and how far the field has gone. So having said that, on Wednesday, we will take some simpler examples because I want to leave you guys with some homework that will help you practice some of these things, sentiment analysis and entity resolutions and so on and so forth. A little taste of everything you get to do in your homework and in the guided lab. However, when we do the 1 month of NLP, then the 6 weeks of it, then we are going to do it in a much more intense way. Everything here is just introducing you to the fundamentals. We are going to do a lot of in-depth practical examples. So wait a minute. By the way, that also raises another question. And but before that, let me stop the recording. The theory part of the session is over.